So I wanted to, for reference, if you hadn't seen this before, which is totally fine, this is the GitHub repository that's going to house all of the information from my workshops. So for this series, I'm going to paste this link in the chat. So the general idea is that any slide deck that I've used or will use can be found here, at least the code for it. Also, what's going to be important is that for each of the individual workshops, all of the data will end up being able to be found inside of a data folder. And I will go over how to take that data. So instead of downloading it and dealing with your own local repository, or if you are choosing to use Google Colab, which is what I'm going to be using today, you don't have to upload or anything like that. We're just going to pull directly from GitHub, right? So it's just a good, powerful tool that you can, or powerful procedure that you can do to bypass needing, any like local versions of the repository or anything like that. Okay. So for reference as well, if we go down to the schedule, so there's some details on why we're doing this. The schedule has the up-to-date version. So I have decided to push out, kind of expand the next concepts that we'll be covering after this workshop. So like LSTMs for sequence modeling and then transformers, they really need their own lectures conceptually and applied. And then we'll only cover a conceptual RAG model. It's kind of like why you would use it. So it's just a reference. Otherwise, well, we're into problems like we had last time where essentially we ran out of time. So for the actual, if you're in this repository, if you want to access the data for today, you can go into slides, data, click on this xor.csv. So the XOR data set is a kind of a classic example of how you can't linearly separate data, which we'll visualize that as well. So you can't directly pull it from here, but there's this raw button. So when you click raw, this is a raw CSV. So this is the actual comma separated variables file. All right. So you can click on the URL and copy it. So when you do that, you'll be able to, inside of the Jupyter notebook that we'll be using, or if you choose to use Python script, which is completely fine as well, you'll be able to just put this inside of a read CSV argument, which we will do, right? So to get started, I know it seems like a lot, but this is really only the text that's describing each of the components that we're going over. The code is completely empty, so we're actually going to be live coding those components, okay? And I'll walk through kind of the justification for each of the steps and why we're doing it, okay? So for reference, this is kind of like a very soft introduction into deep learning with PyTorch inside of Python. So the reasoning we're using PyTorch is it's a pretty robust tool that allows you to utilize what are called tensors. So that's essentially a more sophisticated version of a NumPy array. You can think of it as that it's a multi-dimensional piece of data that allows you to, in essence, do more complex tasks in deep learning quicker. That's kind of the long short of why we're doing it. And for reference in the chat, I'm also going to paste that URL so you don't have to go hunting for it for that CSV file. Okay. So what I want to mention is there are some Python libraries that are required for this workshop. So there's two ways primarily to do installations for Python libraries. I typically use the command line terminal with pip, but you can also do it typically inside of Python, right? So all of this code is annotated out. I will paste it into the chat. All you'll have to do is remove these little hashtags. So I'm going to actually also increase the size. There we go. So you can remove each of these little hashtags. And then this is now a working script. So I usually have some sort of an annotationed out set of installations. If you then, let's say you're using Python, you can run it normally like you would in Python. If you're using Jupyter notebooks that have code cells, run cells, you can click run the cell. And I'm not going to do it, but, well, I can, it doesn't really matter. I've installed everything. So when you run it, it's going to go through iteratively and determine whether or not each of these libraries have been installed, okay? So also note we haven't loaded them yet. We're actually going to do that explicitly as the first live coding step. Yep, so then it's telling me that I already have satisfied all of these criteria. So essentially it's saying everything has been installed. What's nice is that Google Colab has pretty much most of these by default, all of these libraries. So for reference, Torch incorporates the PyTorch library. That's going to have the deep learning framework that is being utilized more and more over, say, TensorFlow. Usually I find that that's because it's a little, maybe not simpler is the best answer, user-friendly perhaps. You can also use PyTorch Lightning, which is a much more abridged version and lets you edit certain things like the evaluation criteria much more dynamically than what PyTorch allows by itself. It kind of goes beyond the scale of what we'll be doing today. We'll be doing a much more simplified version of utilizing PyTorch. That's just for reference. Scikit-learn is the default library in, well, a best practice library for machine learning in Python. Pandas is great for data wrangling and data analysis, so we'll be using it to read in a CSV. NumPy is going to be for array operations, so it's probably, yeah, so standardly, it's good practice to take the columns that you're utilizing in machine and deep learning and converting them into NumPy arrays because it works faster, and typically scikit-learn and PyTorch are going to require that for it to actually work anyway. We also have matplotlib because we're going to do a plot. And then this is not a required package, but this watermark package, what's great about it is watermark allows you to say, well, what were the different versions of each individual module that we utilized instead of Python, okay? So I will just go back. Okay, so let's get started. So I find that it's best practice to have all of your libraries loaded at the top of the page, meaning you've done all of your loading in one code cell, right? So this is, there's a trade-off, right? It's more convenient to have it this way. So, you know, everything is in one place. However, the compromise could be that perhaps you like having individual libraries loaded right above when they're going to be utilized. So for the sake of this workshop, we're going to keep it all in one location for simplicity's sake. So we need to import specific classes from PyTorch. This is because we're actually going to be installing specific functions, so neural networks and some optimization algorithm, which is using what's called backpropagation, which wasn't covered. We ran out of time in the last workshop. Backpropagation is the ability for your algorithm to retrain itself and adjust the weights, so the individual links between the layers nodes. So it readjusts them based off of some sort of penalty. Loss function is what it's called. And the idea is that it's trying to adjust the weights so that over time your loss function is small, right? So you want low loss function that equals to higher accuracy. All right, so first we need to import Torch because we're going to be utilizing PyTorch a lot. We're going to import torch.nn as nn. Only thing I don't like about dealing with these IDEs is it always wants to show me all of these little pop-ups. Import. So the NN is going to be neural networks. So we're going to be using a relatively straightforward neural network in this case, which we'll we'll create some parameters for. We're going to import torch.optim. So this is the optimization algorithms as optim. So this will use gradient descent, probably is the most likely default one. So mathematically, it's trying to reduce that loss function by adjusting the weights. We're going to say from torch.utilities.data, import the data loader comma, tensor dataset. So what the data loader is going to allow us to do is, instead of doing all of the manual components of loading the data into the neural network, you can tell the data loader what you want to occur. So instead of having to do normalization and a bunch of different tasks inside of the neural network, you can do them in a data loader, which then will work kind of externally to what's going on inside of the neural network. This makes things quicker, much quicker, and much less redundant, as you're not having to code what you're doing with the data over and over again. It's kind of similar to a pipeline, as we can think of it. All right, so next we're going to import preprocessing. So this is really the main thing we needed from scikit-learn. We need to preprocess our data set. So a lot of times you want to, in this case, we're going to normalize the data set with a standard scaler to have everything on the same 0 to 1 scale. This is because different scales can bias our machine learning algorithms results just by artificially having a different scale. We're going to say from sklearn dot preprocessing import standard scaler. We then need to import pandas and NumPy. So we'll say import pandas as PD, import NumPy as NP. Oh, and for reference, I will have the actual Jupyter Notebook on GitHub as well. So let me just double check. It might even be there now. So if we go AI healthcare, let's go into notebooks. Yep. So if you're in the main page and you go into notebooks, this is the Jupyter Notebook that we're going to be recreating, right? So if there's any point where perhaps I'm going too quickly, or if you want to work through this later, you can have access to this notebook. And I just put that link into the chat for you as well. Okay, next we need to import matplotlib, loblib, import matplotlib pyplot as plt. So we'll do this for now. We don't really need the watermark step. Let's import them. All right, it looks like that all worked. So if you've installed everything here, the importing step should work without any major concerns, right? So if there are some problems, I would recommend potentially installing these inside of a Python environment. So this one by default has, this kind of is covered inside of Google Colab without any concerns, but it's something that you might have to do if you're running into some dependency issues that can occur. Okay, so our next step is we're going to be loading what's called the exclusive OR gate data set. So it's basically a logic gate that is outputting a 1 when the inputs are different. So 1 is true, the other is false in this case. And it's a classic problem in neural networks because it highlights the limitations of what are considered simple linear models, like anything like logistic regression, for example, or perceptron is kind of the classic example that is putting a linear fit across the variables. So we'll end up taking a look at why this might be a problem. All right, so we're going to say XOR equals pd.read_CSV. We're going to, no, okay, it should be fine. We're going to then go and copy. So it's in that chat for you. I'm just going to copy it from here. We're going to read in that data frame. So let's do that. Okay, it looks like that worked. We can check by saying XOR.head. Yeah, so it read it in for us. So in this case, we do have some class labels, 0s and 1s. So we have, in this case, data set that we know what the classes are. And then we have X1 and X2 are our 2 variables that we'll be looking at and trying to classify, okay? So in this case, It's best practice to convert, as I was mentioning, target variables into NumPy arrays before implementing them. So this helps with compatibility. So PyTorch and TensorFlow, for example, are looking for NumPy arrays to actually utilize data within their functions. It's much faster to process this with lower memory usage on your computer, which is great for things like cloud resources, because in this case, we don't have a lot of RAM and anything that we really are dealing with here. But what's nice is it looks like it is using my computer's, system level RAM, which is good. So it also helps with uniform data types and shapes. So this can help with reducing errors because we're dealing with matrices in this case instead of data frames. So it has a different way that it's being utilized in Python. What's great is you can run things in batches with NumPy arrays. So this can basically, it's called batch processing. So it's great for training models, so batches can be like epochs or inside of epochs, the batches could be you're partitioning up the data into individual batches. It's running through each of those batches until it runs through the full epoch, or an epoch is a full training through the data. And then lastly, it has interoperability, so it's going to be able to convert to things like tensors. So that's what PyTorch is using, and that really makes things flexible. So this can be done relatively straightforwardly. We're going to say x equals XOR. We're going to say in two brackets, quote x1, comma x2 dot values. So we're just looking at the values within this, and then our y is going to equal x or two brackets, or one bracket in this case, because we're not doing multiple indices. We're going to say class label values. So now we can look at print x, print y. Yeah, so we can see that this is converted to a matrix, an array in this case, instead of having a column level variable. So this is going to run much faster through our functions. And it's going to be interoperable, which is the biggest concern. Okay, our next step is to visualize the data set. So we want to, in this case, visualize the problem. This isn't necessarily a required step for deep learning, but I do like to try to disentangle relationships, and you can do that effectively with exploratory data analysis. So in this case, we're gonna end up doing a scatter plot, and we're going to utilize X and Y. So we're gonna go from the arrays instead of the data frame, right? So it's gonna look a little, well, more complex than if you were to just do it from a data frame, but it can be effective to do it, or at least understand what this would look like. So in this case, we're going to say plt.figure big size equals parentheses 6 by 6. So it's a 6 inch by 6 inch roughly figure. So this is a global, or I guess in this case, it's a localized feature for this plot. So this plot that's going to be run will be symmetrical on the axes. So it's not going to have like a stretched out x-axis compared to the y-axis. So this is helpful because this specific data set has symmetry. So it's good to see this. The first thing we're going to do is say plt dot scatter, because we're creating a scatter plot. Within x, capital X, we're going to say y equals 0. And have another bracket, colon, comma, 0. So what this is doing is, in this case, the y versus x, it gives you marker sizes. So we're able to determine, in this case, if this is, what it's trying to do is say, here's this first value here, the x1. Right, so it's the equivalent of saying do x1. We're going to say x, y equals 0 again. So if this is 0, this is that first column. So it's this column here, x1. And then we're also going to want to look at x2 in this case. So to do that, we'll say colon, comma 1. And in this case, this is label equals class 0. So this y equals 0 in this case. So this is coming from, this is x values for any case where y equals 0. So it's filtering out values where you're going to have zeros in this array. So it works, it corresponds that way because they're the same shape. So you can go and say, well, value 0, 0 here will correspond to value 0, 0 here. But in this case, we're filtering out values of x where our class label is 0, all right? And what's happening is on the x-axis, we're looking at the first column, which is column 0. When you have a colon, comma, 0 here, it's all values, all rows, basically, comma. The 0 would be that first column. Again, x where values of y equals 0, and then y is going to be x2 in this case. So x1 is the x-axis, x2 is the y-axis. Okay. So if we take a look at that alone, we're going to find that it's probably plotting, yep, the first half of our problem. This is linearly separable, of course, but we're going to show that in the case of this second scatter plot, it is not the case when we incorporate that values. So you can copy and paste what we just did. All we're changing is y equals 1, so class label 1. We can then take a look and see that we have our non-linearly separable problem in this case, right? So you can't just kind of cut this down the middle here or here. There's no linear separation. It would have to be more of like a polygon that's saying this is the first one, this is the second one is here and here, or something along those lines, okay? And what we're going to be doing is finding what that fit would look like to the best of the model's abilities. So it's going to be difficult because there's some overlap, but we're going to get pretty close. Okay. So we can also add plt.legend just to give us a little more clarification here. Class 0, class 1. I'm not going to do any labeling other than that, since this isn't the data visualization lecture, but you could do this with plt.x label or y label. And that could give you an x and y axis labeling, okay? So our next step is to go through just one preprocessing step, but then converting our values from NumPy arrays to tensors, which is what's compatible with PyTorch. And what's nice is it's a direct transfer in this case. Okay, so in this case, we're normalizing our data, which is going to give us a 0 to 1 scale, that they're going to be on the same scale in this case. It's not explicitly necessary, but in this case, it's just best practice. It's good to do this anyway. So let's load the actual scalar we're going to be using and then normalize it. So we need to say scalar. So this is what we're using to scale the data, equals standard scalar, parentheses. We're then going to say x normalized. So the x values are going to be normalized with scalar dot fit transform x. So this is saying use the standard scalar, fit and transform it to the x array in this case, okay? So when we do this, we can see x normalized. Let's print this out just to take a look. Yep, and we can see how that's different. Hopefully it's different from x. Yeah, so in this case, you can see that it didn't change anything explicitly because it's already scaled effectively, and that's okay. It does tell us that it's not utilized and useful in this case, but it's still good to go through the normalization process to make sure that it is done, right? And then you can have this code for other data sets that don't have a normalized set of variables. But we could see here that our class labels ranged from, or the values range from 0, -2 to 2. Similarly, 0, 2 to -2. Okay. So redundant, but it's still important to know how to do this. So this case, we're going to label this normalization. The next one we're going to say is converting to PyTorch tensors. Tensors. I'm sure I'm pronouncing it the wrong way that I'm not supposed to, but that's okay. We're going to say x underscore tensor is equal to torch dot tensor. So we're creating a tensor from x normalized, comma, the data type, d type, an equal torch dot float 32. So it's a float variable because there's a decimal, and then 32-bit is what we're going to utilize in this case. We can then convert y into a tensor as well, or create one as equal to torch dot tensor y dot reshape. We want to reshape it into a -1 to 1. So this returns an array with the same data in a new shape. So -1 to 1 in this case. So it's going to give us a similar shape that we find with this value, with our original x normalized in this case. And we're going to also say that the data type, d type, is equal to torch dot float 32. Okay, so then it's going to be the same data types. Let's make sure this is running correctly. Yep, looks like it's not mad, which is good. Let's now create a data loader for batching, right? So this is going to allow us to go through individual batches of our data so we can create a certain number of batches to run through each of these processes that we're going to be doing in the neural network. So batching allows for, so think of it as if you ran the whole data set through the neural network without batching it into smaller subsamples, it's going to be much more computationally expensive. So batching is a way for you to break the data set up into smaller partitions. In this case, we're going to determine that the batch size will be 4. So it should be 4 batches. And then we can, it'll shuffle the data each time, things like that. But the idea is that we're getting a good representative sample of all of our data, and it's able to do partitioning much quicker. So we're going to say the data set that we're using is a tensor data set. And we will be using x tensor, comma, y tensor. This is the tensor data set that we're going to be creating. Our data loader is going to be equal to data loader, the data set. And then when we see batch size equals, so the batch size is optional. It usually is 1 batch, so it's running through it once, or 1 partition of the data. We're going to be partitioning it into 4 batches. Shuffle equals true. So it's going to shuffle the data around before doing the batching. All right, so let's run this. And we have a problem because batch size needs an underscore, which is why it didn't like that. Yep, and we're good now. Okay, so before moving on to actually building our neural network, training it and testing it, what questions do we have about what we've done so far? Either in the chat or feel free to unmute as well.
I had a,
Yeah, no, go ahead, Les.
I had a question about kind of clarification of the difference between a pandas setup and an array. Why it was so important to switch from I guess you said pandas data frame, which I guess would be a series of columns and rows where you can clean up the data and manipulate the data and create new rows and so forth. But then how is the array more useful?
So the array is going, so there are two major rationales. So arrays are matrices versus them being in a data frame format. So you can break it up into, when you break it up into a matrix operations are faster in using NumPy just as an example, than utilizing data frames. So data frames, it's basically a string together of vectors. Each column's its own vector. You can take those individual columns, look at it as an array, which would be a vector in a sense, and it will run through your computer much faster than in the data frame format. So pandas is just a little slower. So that's a rationale for why people convert over and do certain operations in arrays. For the sake of machine learning, this is important because um, that speed becomes much more paramount when you're running things that are more computationally expensive. So machine learning tasks can take quite a lot of working memory because certain algorithms, one example being that's pretty egregious at this is k-nearest neighbor. So it's storing all of what it's doing inside of your working memory. So that entire list of neighbors that it's calculating for every single data value is in working memory. So anything you can do to limit the impact of your working memory is beneficial. So the biggest thing is converting to a matrix. It can run through these machine learning algorithms more efficiently. So the second part is for the sake of why they're great for converting into deep learning models is that deep learning models in PyTorch and then also in TensorFlow basically by default are using matrices because of this fact, right? So if you were to run the same thing and basically tell it, take this pandas data frame, here's my X and my Y, run through this deep learning algorithm, it would first have to break them apart into vectors and do the array operations. Or worst case scenario, it would, try to do it on that data frame, which would be pretty slow, devastatingly slow. So the arrays convert to tensors, which are a multidimensional data frame type that works in PyTorch. So you can layer different things on top of each other. In this case, our X tensor has X1 and X2 layered on top of it. So it's basically a two-dimension, it has a multidimensional matrix in that case. And that runs much faster than separately looking at data frame columns. Is that helpful?
Yeah,
This,
absolutely. Thank you.
sure. Yeah, there's more technical, like why computing works a certain way information as well. So if you're interested in more information on it, feel free to email me and I can provide some resources. But that's the gist on why is the short answer is it's much slower to work with pandas.
And can you talk to the need to reshape Y? Like,
Um,
is it going from a single row vector to a column vector, or why the need to reshape Y?
yes. So we are reshaping this because, yeah, it's going from a one-dimensional vector to a two-dimensional vector in this case.
And what is the advantage of that?
So you need to have the dimensional shapes the same when you're looking at X and Y. So if we
Okay.
weren't to reshape this in this way,
Mhm.
it would be incompatible with comparing it to X.
Okay.
So in this case, since we have a Y, our Y is the classification variable. So it's pretty standard to say reshape to this -1, 1 framework here. And
Okay.
then that, we have multiple X's or whatever that might be, and it's okay.
Hey, thanks.
Mhm. Okay. Yeah, these are great questions. I appreciate it. I'm just checking the chat. Oh, we're good. Okay. So let's move on to building our neural network, right? So we're going to actually, so it would be considered a simple network. So technically it's the simplest version of what would be considered a deep learning neural network. We're only utilizing one hidden layer, and that hidden layer is going to have sigmoid activation functions, right? So the way with the neural network, it'll allow the sigmoid function to be able to partition the 0, 1 up effectively without it being limited to what logistic regression can do, which is linearly separate the data, right? So the first layer we're going to be doing has 2 input features and 2 hidden neurons. So it's going to go from input, shoot to the neurons that are hidden. The second layer that we're going to be dealing with has a single value to predict the class. So it's going to look like 2 to 2 to 1, which is the inputs that we're going to be doing. So a more sophisticated neural network would have several more layers, and I could have done that, but it scales up extremely fast computationally. So if we had more hidden layers, it probably wouldn't run very quickly in Google Colab. And even at that, I had to run a very simple, a very limited size number of runs through the training loop because it was taking forever. But either way, we're going to now say we have our neural network. So we're going to say class. Are you using a CPU now? Yeah, right. Yes, I am, Randall. So it would cost, I'm using the resources that are basically available on my computer. So I don't have GPUs that can be utilized through PyTorch. So this one frustrating thing about PyTorch is that it's not compatible with ARM GPUs. So I have an ARM Mac, so I think mine's an M2 chip or something. So I have GPUs. It's just that they're not compatible with PyTorch. It requires specific types of GPUs like CUDA, which are found with NVIDIA GPUs. So yes, I have to use CPUs, unfortunately. But if I was running a much more complex problem, I would be running GPUs on either the HPC or through something like Cyberse, which of course, you have to pay for sometimes for the allocation, but that's also the other thing. I don't want to pay for it, at least for this workshop. Okay, so we're going to create an XOR net. It's basically a network that is standardized to deal with this type of problem. Let's say neural network dot module. So we're creating a class, so we can go down a line and say define 2 underscores init. So initializing basically itself. So we want it to initialize itself as a module. Creating this superclass. So superclasses, it's really going to be the way. I don't have a good definition of a superclass. Carlos, do you know a good definition for a superclass in Python?
Not from my head, no.
Yeah, I was like, I know I heard a definition. I just know that they're utilized in PyTorch for neural networks pretty much exclusively. But whatever, we're going to say it's a superclass XOR net dot self. And we're going to do dot init. So it's initializing itself. We say self, which is basically saying initialize and do work with yourself as a neural network. FC1 is going to equal, so self dot FC1. Oh, here we go. The class from which a class inherits is called a parent or superclass. Okay, yeah. So a class which inherits from a superclass is called a subclass, also called an heir class or child class. So this is where we're getting into like class-based programming. So that means, yeah, this is the class that everything is going to be inherited from. So it's making sure to utilize this XOR network then. So the FC1 and neural network.linear. So it's a linear neural network at 2 by 2 in this case. So this is from a tensor float 32. So if we go down, gives you an idea for the size in this case of our linear partitions, and then the number of initialized bias. We have the weights. So what this is allowing us to do in the case where we have these initialized values, we're only using 2 by 2. So that's where we're starting from in essence. So FC2 equals neural network linear. The second function through that we're going to do is a 2 by 1. Give me 1 second. I'm going to look up in a long week. I need to look up the clarification on FC1 and 2. Yeah, okay. So what this is saying, these are fully connected networks. So when you have these neural networks, you want them to have, every node is connected to each layer, and then each node's relationship with another node is going to be those weights, right? So in this case, we have FC1. So X is going to be passing through this first layer, where then that output is passed through this. We have, I think it's within, get my functions. Yeah, so the next step that we're going to be doing is it's going to be passing through that sigmoid function. So let's write out what this full thing looks like first, and then I can describe it further for you. So we're going to say define forward. So this is a forward network, so it's moving in the forward direction. It's not backtracking. It's moving across the network in one direction. Forward feeding is what's called. We're going to say self, so it's that neural network from above, and X. That's where we're defining what X is going to be. X equals torch.sigmoid. So it's going to be going through a sigmoid activation function in each layer. We're going to say self.fc1 X, and then X equals torch.sigmoid. So this doesn't have to correspond to our X and Y yet. We're just defining what this looks like, right? So think of it as like writing a function that's going to perform some operation. In this case, we're performing sigmoid activation functions within a fully connected simple neural network with one hidden layer, and then an input and an output layer. So let's say self.fc2 X, and then we'll return X. So it's returning the outputs of the layers. We then say model is going to equal X or net because we just created it. Okay, so let's walk through this a little more thoroughly. Okay, so we have our neural network class. So that's coming from PyTorch. So that's going to have the different functions for building our neural networks, such as this neural network module, right? So this will allow us to train custom networks instead of having to rely on defaults. So when we say, in this case, our custom network we're utilizing is this linear one. So that's going to be fully connected dense layers. So it's connecting them linearly. And in this case, that's where we get this fully connected layer 1 that we're looking at, fully connected layer 2. So when we initialize, it's constructing the class for us, FC1. So this line is taking that fully connected layer with 2 input features. And so that's the 2 inputs. So you customize this with how many inputs you have. So we have two inputs, which are x1 and x2. And we have two output features, which in this case is going to take in x1 and x2 and then output it to another layer that has two individual nodes, right? So think of it as it's going from a dimension of 2 and 2 to another dimension of 2 and 2. Then that second layer is going from 2, 2 to 2, 1, right? So 2 to a 2 and then a 2 to a 1 is, I suppose, the most straightforward way I can explain it. And in this case, this is that second layering of weights that's occurring between the single hidden layer that has two nodes. So it's a 2 by 1 because it has one output that's going to our output nodes. Okay. Next, we have to do, this is the forward pass method. So it's a forward directed network where in this case, it's flowing from the input to the output. Our sigmoid functions are going to have a sigmoid activation. So it's really crucial for working with this kind of linearly, nonlinear data. So these sigmoid functions are going to have a distinct probability that each point coming in from the input is in whatever the output is going to look like. So it's partitioning up. It has a hidden component, so we don't know exactly what it transforms the data into. The output component is going to take whatever's in the hidden layer and produce our 0 and 1 desired outputs, right? So it's trying to figure out how do we go from these inputs to the desired outputs, and we'll end up utilizing this simple neural network for this. And next, we need to actually go through the process of training the network, right? So we're going to do the forward pass, we'll compute the loss and back propagate the error. We're going to allow it to train itself after each training loop, right? That's where it's going to be updating any biases or updating any weights. And we'll be monitoring the loss over time. So we'll be ideally seeing it getting smaller and smaller, okay? We're using 100 epochs because it's too expensive computationally to go through 1,000, for instance, which is what I had tried to do before. So we're doing 100 passes, but typically you're going to want around 10,000 epochs. So it'll converge, which is great, but 10,000 is a good baseline. So let's say the criterion, we're going to define loss function and optimizer. Criterion equals neural network dot mean square error loss. So we're going to be looking at the mean square error, which is in the linear, when you're trying to separate anything linearly or in regressions, it's essentially the amount of error between the predicted point and the actual point. So you want to decrease that error as much as possible. So we have mean square error loss in this case. We're going to use an optimizer equals optim dot SGD. So it's gradient descent. This is going to back propagate. It's going to retrain the weights of, between the two sets of layers. We're going to do it by model dot parameters, comma, the likelihood ratio. I think that's what this says. Yeah. Equals 0.1. Learning rate, sorry, not likelihood ratio. So the learning rate's at an increment of 0.1. Okay, so let's train the network. We're going to say for epoch in range, in this case, we're going to do 100 epochs, so 100 passes through the data. Colon. We're going to say for, so this is kind of the difficult part of programming with deep learning models, is there are multiple for loops usually. So for batch X, comma, batch Y, so for each of the batches from or in our data loader. Now we don't have to do all of that inside of this training loop, right? It's external, so it's going to be much more efficient for us. We're going to say optimizer I'm gonna optimizer dot 0 grad. So it's resetting the gradients of all tensors, at least in the beginning. Our output equals model batch X. The loss is equal to criterion from the output, comma, batch Y. So this is going to be, the output is what it's predicting for the individual output values. The batch, this is the truth. This is what is the actual output, right? And it's going to be comparing. So then we say loss dot backward. This is going to say, well, we've learned that our loss is, you know, maybe it's high. We're going to go back and retrain the weights based off of what our loss was in this case. And then optimizer dot step. It's just saying that you have to do the optimization step. So now we say if epoch plus 1. So this is going to, this information here is going to tell us how things are going, essentially. If it's epoch, if epoch plus 1 is 100 in this case, so it's every 100, whoops, every 10 epochs. So as long as, if that equals 0, then print, go one more, tab, print. F is going to print out the specific components that we want. So we're going to be saying print epoch. Anything inside of this curly bracket is going to be pulling directly from function that's being read in. So it's the epoch plus 1, comma, loss, colon, curly brackets again, loss dot item. Okay, so this is going to run through and update us at every 10 epochs. What is the actual loss? Okay, so if we run this, if it doesn't break, it's going to take a moment. Yeah, so our loss is already pretty low, and then it kind of shoots up here. It's lower again. Yeah, so 0.002 for loss. Smaller numbers are better. So this is good. For our last 5 minutes or so, we're going to actually convert this here, this final loss, into what our actual testing accuracy was. So it's where we're doing evaluations on how well this went. So with torch.no grad, so it's pulling from what we just did. So it's giving us an idea of how well things were predicted. Predicted equals model X tensor. So this is the predicted values, came from this set of X values. Predicted equals, if predicted is greater than 0.5, dot float. Or not an F, it's just giving us predicted values that are greater than 0.5 because we want all of the positive. So the 0.5 prediction is coming from sigmoid function. So if it's greater than that 50 percentile, which means it's equally probabilistic to be one or the other. In this case, we're trying to test whether or not it's giving us the correct ones, in essence. So we're going to say then accuracy equals predicted double equals to, it's exactly equal to y tensor. So this is when predicted is exactly equal to the y value, the truth sum, so add them up. And then item is going to just basically say, well, this is the actual value, the item. We're going to divide that by y tensor dot size 0. So that's going to give us how big the data set is. So ideally, if accuracy was perfect, this sum, meaning that when predicted value was equal to the tensor, the actual value that we want to find, if it was summed up, if it was exactly the size as the tensor, our y values that we want, it would mean the accuracy is 100%, right? So we'll end up now seeing print function. We'll be looking at accuracy, colon, accuracy, multiplied by 100%. So this will give us the accuracy for our neural network. And it was 95.333334%. So quite good, right? So it's able to differentiate what we're looking at very well. Otherwise, if there were some issues like with, maybe we want our learning rate to be lower. So let's take a look at what that would do. It might or might not have an effect, but there are just certain hyperparameters that you can tweak. So we'll just run through this, which will be in that one last minute. And then, yeah, accuracy is pretty much the same, right? So in the case, it didn't really have a major impact. But all right, I only have you for less than a minute, but I can always go into a breakout room for additional questions while the next workshop goes. It's always tough kind of wanting to not give you too much information because we run out of the hour quite fast. Yes, Randall, everything is on GitHub. I made sure to have the notebook already there for you, so I'll paste that link again. So this notebook has all of the code that I just went over. Okay, that's my time. So Carlos, feel free to stop the recording. I will